Welcome to section 7.2, graphing quadratics functions in standard form. So we're going to be focusing on f of x equals ax squared plus bx plus c. And in this form we cannot tell what the transformations are, so we can't tell what the vertex is. And the thing is, a vertex is important. When we're graphing a parabola, we have to have the vertex definitely on the graph, and then any y-intercepts or x-intercepts. Okay, so our goal then is to focus on the first one, the vertex, because we know how to find the y-intercept. We can find the y-intercept by plugging in x equals 0, and the x-intercepts we find by letting y or our function be 0. So we have to focus on the vertex. So how we're going to do this is we're going to complete the square. So to demonstrate that, let's look at x squared minus 6x plus 7. If we want to complete the square, we want to write all of our x terms as a perfect square, so something like x minus h all squared. And then we'll know the vertex. We'll know that the vertex happens at h comma k. We learned that last section. All right, so let's take our function x squared minus 6x, and remember we are completing the square on the x term. So we're going to add a constant that makes x squared minus 6x a perfect square trinomial. All right, and then we have our plus 7. And we know how expressions work. We're not allowed to just add a number. So whatever number we add in the red, we have to balance our equation by also subtracting it. And now we haven't changed x squared minus 6x plus 7. All right, so essentially how perfect square trinomials work is we take our middle term and we know half of it squared is going to be the constant. So we are going to divide it by 2 and we're going to square it. So this is going to be negative 3 squared. So the constant required to make it a perfect square trinomial is going to be 9. And again, if we add 9, we have to subtract 9. So x squared minus 6x plus 9, this is now a perfect square trinomial. So we can factor it like this, and it's going to factor as x, and then whatever's in the parentheses, minus 3, all squared. All right, and then what's left over is the plus 7 minus 9, or negative 2. Okay, so for x squared minus 6x plus 7, if we wanted to graph it, we would have vertex 3, negative 2. And we saw that in our last section. All right. So let's continue on, and we're going to have a formula in general. So we're going to complete the square for any quadratic function, ax squared plus bx plus c. And then hopefully we get a formula for the vertex rather than having to complete the square each time. Okay, so when we complete the square, we are going to have to make the coefficient on our x squared 1. So ax squared plus bx plus c. So remember, we're going to complete the square on the x terms. Before we do that, though, we want our coefficient on x squared to be 1. So we're going to factor out an a. So when we do that, remember that's like dividing each of the x terms by a. And we get this. And then we're going to do a constant right there to complete the square. And then on the outside, we still have our plus c. And then remember, we have to balance, so we're going to subtract whatever we add. And then that's going to keep everything nice and balanced. Okay, so when we complete the square, how perfect squared trinomials work, the middle term can get us back to the constant if we divide by 2 and square it. All right, and if you're having a hard time seeing that, we can do some work really quick. Like this. Remember when we have the x plus a squared, so we're working backwards. If we FOIL that out, that's x squared plus 2a plus a squared. So for perfect square trinomials, how the middle term and that last term relate is we can take this and divide it by 2 and square it, and that will always get us the constant term. Okay? So if we see that, let's continue on, now that that's a little clearer. And for this general case, so again, we're slowly figuring out a formula. We're going to take the b over a, divide by 2 is like just putting the 2 in the denominator, and squaring it. So the constant we need is going to be b squared divided by 2 squared over a squared. That's going to go right there. B squared over 4a squared. Okay, and we have to balance it. So whatever we add, if we add a b squared divided by 4a squared, we have to subtract the same quantity. But before we subtract just a b squared over 4a squared, remember it's eventually going to get multiplied by this a. So when we multiply it by the a on the bottom and the top will cancel. And so to balance it, we're going to subtract, and I'll rewrite it all on one line, just b squared over 4a. Okay, whew, this is a lot of work. Let's write down what we have. So ax squared plus bx plus c is the same as this by completing the square. Then we have plus c minus b squared over 4a. All right, and really what we're interested in is where the x value is for our vertex. So let's factor this as a perfect square trinomial. So the constant's going to be the square root of the b squared over 4a squared. All right, all squared. It's also the inside of the parentheses after we divide by 2. And then we have our essentially y-intercept of our vertex, this constant right here. But for our formula that we're developing, and really the only takeaway we're getting from this proof essentially, is this is the x-intercept of the vertex. Let's come down and write our vertex formula now. So for polynomial, for f of x equals ax squared plus bx plus c, the vertex is, and again we just focus on the x-coordinate, and it's the opposite of b over 2a. And then the y-coordinate is the corresponding y-coordinate. You would just plug that into your function. So you can write it like this, if you'd like. But it's just the corresponding y-coordinate. So let's see where this gets us. So let's go back to x squared minus 6x plus 7. So if we wanted to graph it, we have to have the vertex. And now we have a formula, negative b over 2a. You can always kind of complete the square from scratch too if you don't want to use the formula, but I think it's a little bit easier to use our formula. Okay, so it's the opposite then of b. So b is your middle term, -6, over 2a, where a is your leading coefficient. Okay, so it's, let's see, -6 over 2 is -3, so the opposite of -3 is 3. So we don't know the y-coordinate yet. So now we're going to plug in 3 into our function. So 3 squared minus 6 times 3 plus 7. So 9 minus 18 is -9, plus 7 is -2. So 3, -2 is your vertex. So let's put that on there. The other thing we need when we're graphing our function is we need, I'll write it over here, we need the y-intercept. We always have a y-intercept. It happens when x is 0. So you can write it like this, f of 0. And zeros are nice to plug in because it makes all of the x terms go away. So 0 minus 0 plus 7. The y-intercept is 7. Ooh. All the way up here. We have to extend our graph a little bit. That's okay. All right, and then finally we have our x-intercept. That's when our function is 0 and we find the f values. Okay, so let's set x squared minus 6x plus 7 to 0 and solve it. All right, so let's see. Middle term is negative. The 7 is positive. So two numbers that multiply to positive 7 and add up to -6. So they both have to be negative. The product is positive. The sum is negative. So our options are 7 and 1. And -7 minus 1 is not -6. And that's our only option. So it essentially means that we can't factor it. This means we're not going to have rational zeros. So we can't actually find the x-intercepts. They're there because they definitely cross through the x-axis, but we can't find them. We'll find them later on in the chapter. Right now we don't have enough information. So what we have here is good enough. If we wanted to do an extra point, we can use symmetry, right? So for instance, our y-intercept up here is 1, 2, 3 away. So we can go 1, 2, 3 away on the right and the same height, right? So we're just creating this nice symmetry. And then we can make our parabola like this. Okay. And there you go. So let's look at some other things about this graph. What is our domain? It's all real numbers. And then what about our range? Y is greater than or equal to -2. All right, and then also what's our axis of symmetry? It's a vertical line. So x equals the x value on our vertex. So x equals 3 is your line or axis of symmetry. So all of these nice things. Let's look at a different example. We are going to graph x squared minus 8x plus 7, and we're going to do the same three things, vertex, y-intercept, and x-intercepts. Go ahead and pause it and then come back and see how you guys did. And welcome back. So first thing, our vertex is the negative b or opposite b over 2a, and then whatever your y coordinate is. Negative b over 2a is the opposite of negative 8 over 2 times 1. So that's the opposite of, let's see, negative 8 over 2 is negative 4. Negative 4 is positive 4. So our vertex is 4. And then whatever f of 4 is. So when you plug in 4, you guys got 4 squared minus 8 times 4 plus 7. So 16 minus 32 plus 7. You guys simplified that to negative 9. All right, so let's see how many tick marks we have on this graph. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It goes down to negative 10. And so all these are 10 by 10. All right, so let's graph that vertex. So 1, 2, 3, 4, and negative 9. Okay, it's small, it's a little bit harder. Then we need our y-intercept. That's when we plug in the 0. And when it's written in standard form, it's just the constant. So 7 is the y-intercept. 1, 2, 3, 4, 5, 6, 7. Okay, you can even do a symmetrical point. 1, 2, 3, 4. There's your axis of symmetry. 1, 2, 3, 4. You can do the symmetric point, the mirror image along the axis of symmetry. And then finally, we're going to do our x-intercepts. Do we have x-intercepts this time? So that's when x squared minus 8x plus 7 equals 0. And this time we do, because that factors as x minus 7, x minus 1 equals 0. And so by the zero factor property, that's when x minus 7 equals 0, or x equals 7, and then x minus 1 equals 0, so x equals 1. So 1 and 7 are your x-intercepts. So there's 1, 2, 3, 4, 5, 6, 7. Okay, and then this is enough to graph your parabola. Try to be as smooth as possible and get that nice parabola shape. And remember to include your arrows because this goes on forever. All right, so in that case, we got to get all three things on there: the vertex, y-intercept, and x-intercept. I did bonus point, the bonus symmetric point, but I wouldn't require that. I wouldn't mark you off if you guys forgot that. Sometimes it's just nice to have that to get a nice sketch of your parabola. Okay, so next we're going to be looking at optimization. We're going to be looking at word problems that use optimization. And optimization means kind of the biggest or the smallest. And it's helpful to do these problems with a quadratic model because a parabola has a maximum sometimes. So when optimizing, we like to find the maximum, or sometimes the parabola has a minimum. And that point happens at the vertex. And we know that that vertex formula is opposite of b over 2a. And then the function value. Okay, so if we have a quadratic model, we can do these optimization problems. So let's look at this first one. A rancher plans to use 400 feet of fencing and a side of his barn to form a rectangular boundary for cattle. What dimensions of the rectangle would give the maximum area? And what is that area? Woof, let's draw a picture. So he's going to use a side of his barn. So this will be the barn. And then 400 feet of fencing. So that barn will probably be one side of the rectangle, and then the 400 feet will be used for the rest. All right, and then we're going to have cows inside. Okay, there's my cow. Those are spots. Let's see how we're going to do this. So we want to find the dimensions. That's a key word. We want to find the dimensions. All right, so that means we can call this y. We can call that x. And that's going to give us the dimension. And it's a rectangle, so those two sides, the y's are even, and the x is just one side of x. Okay, so we want to maximize area. So if we're maximizing area, that means we're going to have a parabola, right? This is our maximum one. So our area is probably going to give us a quadratic formula. All right, so since we're trying to maximize the area, we're optimizing area. That's the model we're going to focus on. That's going to be the quadratic model. Okay, let's write that down. We want to optimize area since we want to find the maximum area. So we know that the area of the space for the cows is going to be the area of a rectangle. Length times width, or in our case, x times y. All right, so we have two variables, unfortunately. And when we're optimizing or using we're trying to graph quadratic, we only have one variable. So we had to figure out how to change x into y or y into x, something like that. And we're going to use the other fact that was given to us, the fact that it's 400 feet of fencing. So remember when we're talking about that, when we're talking about fencing, back in the day we learned that keyword meant perimeter. All right, so we have three sides. We have two y's and an x, and that has to equal 400 feet. Okay, so essentially we have a systems of equations, and we're going to solve for one of the variables for the perimeter and plug it into area. Let's solve for x. So subtract 2y from both sides. And now we'll substitute in our area formula. And so now we have area in terms of y. So we'll write area as a function now, a of y. All right, and then when we distribute that y and clean this up, when we distribute the y, now we see our quadratic function. All right, in this one we don't have a constant, but that's okay. All right, we also notice that our leading term is negative. So that means if we were to graph this, we do not have to graph it, but if we were going to graph it, our parabola would be a sad face. And so the vertex will indeed give us the maximum area. This is our A. So it will give us the maximum area at the vertex. Let's kind of write that out, that logic. So max area is the vertex. Okay. So let's plug in a y, and then we're going to get out the area. All right, so just to clarify, this helps us answer the question, y is a dimension. So we're going to plug in a dimension and we're going to get an area. So when we use our vertex formula, negative b over 2a, that is a y value, which is a dimension. And then since we want maximum area, we're going to have to plug that into our area function. All right, so we just have to keep track of what we're doing. So let's figure out that vertex and then we'll interpret it. So negative b over 2a, so the opposite of 400, that's your b, over 2 times negative 2. So 400 divided by negative 4, and then take the opposite of that, is positive 100. All right, so dimension is 100. And now we're going to have to plug that in to our area function. And that will tell us the maximum area. Okay, so a of 100 equals negative 200 squared plus 400 times 100. All right, and if we work that out, you guys can verify with your calculator, you're going to get 20,000. Okay, so what we have here is an area and a dimension. So let's start writing some things out. And now we're ready to state our solution. So the maximum area this farmer has is what we just found, that 20,000. What are the units? We know area is square, but square what? We had feet, so 20,000 square feet. And then let's talk about the dimensions, because we're also asked to talk about the dimensions. So using the dimensions, let's see, we had y was 100 feet, and x, we had a formula, was negative 2y plus 400, or 200 feet. And that part in green is our solution. And if you wanted to complete your drawing, remember we had our barn, and the maximum area was 20,000 feet squared. The y was 100 feet, and your x was 200.